Material science and engineering, let's see. Part of it is just the thought that everything is made of something, and what really interests me is what that something is, and so how that something can be made better, made more efficiently, have more interesting properties. Is there interesting science about that stuff? And so I guess it's it's basically the stuff the world is made of that sort of is made by humankind. And I have a very general view of materials. A number of people tend to focus their research, say, in metals only, or really focus in polymers, while I think we view the world with a bit of a polymers directed view. It's very much that we like to work with all classes of materials. So if it turns out that polymers work great, wonderful. If it turns out that they're part of a system, that's great. And in some of our recent work, there's nothing at all to do with polymers, except that if you can think about how maybe it was inspired by. And so I guess that's sort of the view of, instead of thinking about materials as one sort of kind of material, it's really the view of, we have to build things from something. That something is a material, and that's just a fun, exciting topic, I guess. So the textbook definition, of course, is polymer, many units. I don't relax that too much. The many, one can decide whether that means is 10 or 100 fine, or does it have to be thousands of things linked together. The units, of course, classically are small organic molecules that are linked together with covalent bonds, but it really is just a unit. So you could have a polymer that was made up of particles on a string, so beads on a string. You could have a polymer that is made up of things that are held together pretty strongly, but maybe not a covalent bond. And so you think about what holds the two strands of DNA together; those are hydrogen bonds. But I would still say it's a spaghetti-like object that is built from building blocks held together in some interesting fashion. So I think that's still the classical definition. I think it's one of the reasons that we keep coming back to looking at polymers is there's just such a diversity in properties that you can obtain in polymers. You have systems that are flexible at 100 degrees below zero. You have systems that are stable up to 400 or 500 degrees Celsius above zero. There's just so many different knobs you can turn. You have, of course, the main chain, the polymer, but then you can hang whatever you want off the side. And so there's sort of a diversity in properties you can get in polymers you almost can't get in anything else. And so when we think about problems, we always come back and say, polymers would be a nice way to do it, because we can sort of tune. You can just keep adding all the function you want. And that's very difficult with many of the other classes of material. I'm a little biased. I was a graduate student here. So I started here in '93, and I did my PhD here, working in the department. In fact, today some of my labs are the same as the labs I worked in as a grad student, so that's always fun. But really it's an amazing place. It's an amazing place from everything from the undergraduates that we get. I teach the freshman course, and so I see these students, they come in, sometimes I'm the very first class that they've had in college, and there's a little naivete at the time, but you sort of see them grow into it, and you're starting. It's a very good starting material, shall we say, and so that's a lot of fun. The graduate students, similar. We just get excellent grad students. I think what makes a great university is really all the things. You have to have great undergrads. You have to have great grad students. As one of the faculty, you want to be surrounded by other faculty who think about really interesting things and sort of, keep pushing you to think in ways that you hadn't thought before. And then you have to have the infrastructure that allows us to teach and do research and all the things that we love to do. And so Illinois has all those things, and when I was interviewing, looking at other places, it's easy to find somewhere else that has great undergrads, but maybe they don't have the right facilities, or they have really nice facilities, but they can't seem to recruit really good graduate students, or they have all the things, but the department's sort of small and doesn't have the diversity. And so for someone like me that likes to work in different areas, it just wasn't going to happen. So in some sense, Illinois has it all. And so that's what drew me here as a grad student. That's what drew me back, and that's what's kept me here. I'll do that at a few levels. In the most generic form, we are interested in how do we improve the function of materials by understanding its 2- and 3-dimensional structure. And so it's the difference between, say, a solid piece of polymer and a polymer foam. They're both maybe made of the same polymer, but in one case it could be a pretty hard, brittle material, in the other case it could be very, very soft and squishy. And so it's the same material, the only difference is how it's sort of assembled in 3 dimensions. And so that really runs through many, many of my projects. Now, when we think about where that leads and what that's led us to systems where we have new kinds of batteries that you can charge and discharge very quickly because we make a foam out of the electrode, and so you can move ions and electrons and all the things that are important for a lithium-ion battery. In systems like self-healing materials, we've learned how to put little capsules of glue in there that break open, and if the capsules are too big, it doesn't work. If they're too small, it doesn't work. And so you sort of have to understand both the engineering and the science. In all of our work about optics, we take something like silicon, which, solid piece of silicon, it's fine, but you start to put structure in it at the right length scales, you can really control the way that light interacts. And so rather than coming up with a new building block, we tend to work with materials which are known and think about how we can structure or shape them in new forms that result in new properties. As an undergrad, I was enjoying research, and so that leads you in the direction of, graduate school. So, at the time you have some idea, maybe a professor is one option, but there's lots of other things. So at that point I wasn't really worried about it or honestly thinking about it. I would say it was probably about halfway through grad school. You realize eventually you're going to have to enter the real world. You can't be a student forever. Grad schools let me put it off for another 5 years or so, but that's going to come to a close. And so I started to think about, what would be fun, what would I find exciting, honestly, what do I think I'd be good at, and as I looked at all of those things, academia seemed to be the right place. And so I spent the last few years of graduate school really trying to make sure that I had done the kind of things you need to do to be successful in applying for faculty positions. And so, depending what you want to do in grad school, you move your research around a little bit, and I tried to move it in a direction that would help me be competitive. So there are a few really fun papers from graduate school, but I think the one that stands out for me was one where we were doing waveguides in 3-dimensional photonic crystals. And so these are structures that allow us to move light. And it may not be the highest impact paper we ever write, but it was really the most serious paper that I wrote as a new assistant professor. And so it was, we came in and worked really hard on something for about 2 years, and in the end it worked, and we got a really nice paper out of it, and lots of people have read it, and it's inspired other people's to work. I'm sure there's things that we've done since then that in the end will matter more, but it was exciting because it was sort of the first time that it was not work where my mentor had suggested a project or my PhD work or I'd been working with one of my colleagues. It was really something that we said, we should do this and this matters. And so that's been out for about 10 years now. It's led to lots of other things, but that's probably the one that I think about that sort of goes, this was really ours. It's the first time we did something new. So in the fall I teach the freshman Introduction to Material Science. This is MSc 182. That's the first course for majors, and it's a lot of fun because everybody who comes in has picked material science, so they want to be there. They, at least they think they want to be there. A few change their mind, but a few transfer in, so that's okay. And so this course has all of our incoming students, and you get to see them develop from when they show up. They don't know what a crystal is, or they barely know what a crystal is. And by the end of the semester, they actually can talk in the lingo of material science, and so that's really exciting. They sort of know the fundamentals. In the spring, for a number of years, I taught Introduction to Polymers. After that, I switched mostly to teaching polymer chemistry, which is a mixed undergrad-grad course. And then starting this year, I'm going to teach the nanoscience, the senior level nanoscience course, and I'll probably do that for a few years. So that'll be my first time teaching that. So I came to Illinois on the faculty in 1999, and really have been teaching since I got here. The one I've taught the most years is the freshman course, and I think I've taught that now. This is, I think, the 7th year that I've taught that course. But typical is to teach a course for 3 to 5 years, and then you move to something else. Well, there's one thing I know they remember, so that's good. In the freshman course, I do the material science of chocolate. And it seems to be that most students remember that if they remember anything from their undergraduate days. I've run into some alumni, and 5 years later, they go, "Oh yeah, I had you the first time you taught 182, and I remember the chocolate class." And then they go, "I don't really remember anything else," but that's okay. I'm sure they do in some sort of subconscious way. I think what I really want students to realize is that we're really only limited by our imagination with materials, that there are table upon table of materials that you can select from, but that's just the starting point. Once you know what puts materials together and what makes materials tick, then you can basically say, I want this function or I want this property, and you can learn how to create a material that never existed before that does that. And so I think that's, once you have that mindset, it makes it so that you can do so much more than someone who simply says, I can take a list of materials and tell you the one to pick. And I think if we can build that into the students, they will really do a lot for them.